Good day, chemistry students. Mr. Schlecker here with another lesson. Today we're going to learn about a chemical concept called limiting reactant. So the objectives for this lesson are we want to be able to actually know what a limiting reactant is, and then we want to see how it affects the products of a chemical reaction. Then we want to be able to determine what the limiting reactant is and what the excess reactant is in a chemical reaction. And then finally, we want to be able to calculate something called the theoretical yield of a product using that limiting reactant here. So what we already know is that the coefficient of a chemical equation shows the ratio of each particle necessary to react. So, for example, here, maybe we need one particle of H2S to react with two particles of NaOH. Alternatively, you can think of it as 1 mole of H2S is needed to react with 2 moles of NaOH. I just answered this here. You need 1 molecule of H2S to react with 2, we'll call them formula units, since it's an ionic compound, formula units of NaOH. Just a 1-to-2 ratio based on these coefficients. This is actually going to be really important looking at these ratios when we're looking at this concept here. So before we even talk about anything, I just want to ask, has this ever happened to you? You want to go out to the movies, but you ran out of money. Well, maybe that money is your limiting reactant here. Maybe you're trying to make a bunch of hot dogs and you ran out of the hot dog buns. Well, the hot dog buns are your limiting reactant. Lots of times your outcomes are limited by one thing that's bottlenecking everything. And that's the exact same thing in our chemical equations here. So let's look at this other little example here of what a limiting reactant could be. Imagine you were creating ham sandwiches, and each sandwich requires 2 slices of bread and 5 slices of ham. It's a very precise recipe. If you were given 6 slices of bread and 15 slices of ham to work with, what ingredient would you run out of first? Okay, so I'm thinking here, 6 divided by 2 would give us, 3 sandwiches worth of bread. And 15 divided by 5, that would be like 3. Hold on. So 6 divided by 3 gives us 3 sandwiches, right? Based on the bread. And then 15 slices of ham divided by 5 slices needed per sandwich gives us 3 total sandwiches possible. So it turns out neither one of these ingredients are going to limit us here. And we can actually, we can write this like in a more dimensional analysis-y way here. And you might see this notation later on. I just want to throw it out there, see if it sticks. If we start with 6 slices of bread, we know that there are 2 slices of bread in one sandwich. So when you do this math here, slices of bread cancel, 6 divided by 2 is 3 sandwiches. Awesome. And then just rewriting the slices of ham using dimensional analysis notation, if you have 15 slices of ham, then in one sandwich, you need, 5 slices of ham. Excuse my handwriting. 15 divided by 5 would be 3 total sandwiches that you can make. That cancels. 15 divided by 5 is 3. Okay. So it turns out there was no limiting reactant there, but what if we are given 6 slices of bread and 6 million slices of ham to work with? What ingredient would you run out of first when making these ham sandwiches? Well, I'm thinking I have a lot less bread than I do ham, so I'm probably going to run out of bread. I'm not even going to calculate anything here. I'm just going to say bread. No bread gotten here. Now, if you happened upon 10,000 slices of bread, but maybe now you ate all your ham and you only have 10 slices of ham, what ingredient are you going to run out of first? I'm thinking ham. A lot less ham than we have bread. And you can just tell that just by the basic amounts here. So cooking recipes are like our chemical equations here. You have to use ingredients in certain ratios if you're following that recipe. I mean, maybe if you're not some master chef who's just making up recipes, but if you're following that recipe, you have to use those certain ratios. And that's just like our chemical equations, where chemicals have to react in certain ratios according to that balanced chemical equation. So those coefficients tell us like, oh, maybe it's a 5-to-1 ratio or a 3-to-1, etc. Now, if you don't have enough of one ingredient, that will limit how much of the final food dish that you can make. So in chemical reactions, you're always going to run out of one reactant before running out of another. So let's look at this one over here. This is a really basic chemical reaction. Combustion of hydrogen gas, also used in hydrogen fuel cells. Oxygen plus 2H2 makes 2H2O, which is water vapor molecules. So any reaction is going to be limited to the least available reactant. So whatever reactant runs out first will limit the reaction from happening. So if we have 1 mole of O2 and 2 moles of H2, is either one going to limit us here? Let's see, if we have one of these and two of these, well, it looks like that's the exact ratio that it's used up in. So we'll say no, neither of them are going to limit us. We have a nice equal amount, a nice proportional amount that we can use. How many moles of H2O do you think will be formed if we have 1 mole of O2 and 2 moles of H2? Well, it actually says it right here, 1, 2, 2. So we will have 2 moles of H2O formed. Okay, if 2 moles of O2 and 2 moles of H2 are available, is either one limiting? Okay, so now we have literally equal amounts of moles of each reactant. But you have to ask yourself, which one is being used up faster? So I'm seeing here that there's a 2 by the H2 and there's only a 1 by the O2. So H2 is being used up twice as fast as O2. So if H2 is being used up twice as fast, then yes, I think H2 is limiting here. So how many moles of H2O do you think will be formed if you just have that limiting reactant? So we're going to look at H2. If we have 2 moles of H2, how much H2O is formed? Well, it looks like it's 2 to 2, so we'll just say 2 again. Now, the limiting reactant is not going to be the one with the greatest coefficient. It's not going to be the one that's used up the fastest every single time. For example, what if we have 1 mole of O2 and 3 moles of H2? Is either one going to be limiting? So we can look back over here and we see that, okay, even though H2 is being used up twice as fast, O2 actually gets used up first. There's just so much less of it. So yes, O2 is limiting here. Whatever's not limiting the equation from going further, we're going to call that the excess reactant. So a life in excess. You have so much extra, it's excess. Just the other one that's not limiting. Okay, so if you're a little lost, but you think you're kind of following along, that's fine. We are going to talk about a very specific procedure so that you can always figure out what the limiting reactant is based on our chemical equation. So what we're going to do whenever we see a chemical equation and we have some sort of burning question, like what's the limiting reactant here? What is it? We are going to take the number of moles available of each reactant. So moles of each reactant, just find that amount in moles. And you're going to divide the number of moles by the coefficient of that chemical in the balanced chemical equation. So you're going to get different numbers for different reactants. The smallest number that you get, the smallest value that you get, is the limiting reactant. And you can express it in units of moles of reactions that happen. So let's look over with that previous chemical equation. And here, I'm just rewriting it here for y'all. If you have 37 moles of O2 and 75 moles of H2, what is your limiting reactant, if any? So I'm looking at these numbers and I'm thinking, these are kind of big. I can't really mental math my way through these numbers as easily as the other numbers. So I'm just going to use my procedure to figure this out. So my strategy is, first of all, I want to make sure that I have the number of moles of each reactant. Okay, I have 37 moles of O2 and I have 75 moles of H2. Seems good. So step one is done. Second step, let's take the number of moles of each reactant and divide that by the coefficient of the chemical equation. And doing that is converting it into moles of reaction. So we can do that with dimensional analysis, just like what we did on the last page with making sandwiches. This is almost the exact same thing. So I'm going to start with O2 first. So we have 37 moles of O2. And I'm going to look at this balanced equation, and it looks like there's no number in front of O2. So I'm going to say that coefficient is 1 mole of O2. So there's one of those O2s in every one reaction that happens. So we're going to call that 1 mole of reactions that happen. So 37 times 1 divided by 1. Now we have 37 again. And be careful with your units. Moles of O2 cancel out. And now we have 37 moles of reaction that happen. So you could think of it as like 37 of these reactions happen with just 37 moles of O2. Okay, not done yet. Let's look at H2. So we start with 75 moles of H2, and let's convert it to moles of reaction as well. 75, let's see, in the balanced chemical equation, we have 2 moles of H2, so I'm going to put that down there. And that's in every reaction that happens. So I'm going to say 1 mole of reaction on top. So these moles of H2 cancel because I have 1 on top, 1 on bottom. And now I have to do 75 divided by 2. Let's see, 75 divided by 2. Let me find my calculator. $75 divided by 2, I'm getting 37.5. And then your units should be moles of reactions that happen, because that's all that's left. Okay, so we have 37 moles of reaction that happen because of the O2 that we have, but we have 37.5 moles of reaction that happen because of the H2 that we had. So less reactions are powered up by the amount of O2. Therefore, the O2 that we have is limiting the reaction from going further. So we are going to call O2 our limiting reactant, because the number that we got, the number of reactions that we got, is less. Which means that the one that we have extra of is the other one. H2 is our excess reactant. And that's how we solve that problem. Okay, let's look at another example. This time we are starting with a number of grams of each reactant. A sample of 10 grams of ammonia, so ammonia is NH3, smelly household cleaner, is mixed with 20 grams of oxygen, O2. Which reactant is the limiting reactant? A balanced chemical equation is given below. Okay, this beautiful balanced chemical equation. Always need that for these reactions, these problems. So first of all, Step one was we got to make sure that we have the number of moles of each reactant. In this case, we don't. We have 10 grams of ammonia and 20 grams of oxygen. So we got to figure out how to get moles from grams. Easy peasy. We just use those molar masses. So I'm going to start with 10 grams of ammonia, 10 grams of NH3, same thing. And we are going to divide by the molar mass of ammonia. Let's see. A molar mass of ammonia, mass of N is 14.01, mass of H is 1.01. So 14.01 plus 1.01 times 3 should be, what is that, 17.01, 0.03, 0.04. Oh my goodness. Mental math is hard. Grams of NH3 in 1 mole of NH3. So now we calculate 10 divided by 17.04. I'm getting 0.587-ish moles of NH3. Okay, next chemical. Let's look at, I'm just writing some arrows here. Let's look at this amount of oxygen. We have 20 grams of oxygen. O2 has a molar mass of 32 because each oxygen is 16, so 16 plus 16 is 32 in 1 mole of O2. So we are going to cancel out those grams of O2. 20 divided by 32. We get something like 0.625 moles of O2. So we are now seeing, okay, look, we have less moles of NH3, so clearly it must be limiting. But wait, we are not done with this question. Do not make a conclusion yet. Let's go to step 2. Step 2 says we got to take the number of moles that we have and divide it by the coefficient. Okay, so let's go ahead and do that. Let's do that a little bit of dimensional analysis here. So starting with 0.587 moles of NH3 divided by the coefficient in that equation, looks like that is 4. So 4 moles of NH3 in every mole of reaction, in every reaction that happens. So moles of NH3 cancel. We have 0.587 divided by 4 to get 0.147 moles of reaction that happen based on the amount of NH3 that we have. Okay, now let's look at O2. Starting with 0.625 moles of O2, it looks like our coefficient here is 5. So we say in every 1 mole of reaction, we have 5 moles of O2. All right, so 0.625 divided by 5 looks like that is 0.125 moles of reaction that happen due to our O2. Okay, now step 3. We are now allowed to make a conclusion. What is our limiting reactant and what is our excess reactant? Well, now I'm looking over here and this 0.125 is looking like the smaller number. So I'm going to say O2 is our limiting reactant. It powered up less moles of reactions than our NH3 did. So that means NH3 is our excess reactant. Okay, we're breaking things up into a lot of steps here. So personally, I like to do everything in just one step using dimensional analysis. So I'm going to just show you how we do this problem again, just in one step or one setup by combining steps 1 and 2. So thinking about how do you convert to moles and then reactions all in the same line of the problem. Like for example, NH3, we started with 10 grams of NH3. And then we're like, okay, we need moles of NH3, so we put the molar mass on the bottom to convert it to moles. What was that? 17.04 grams of NH3 in 1 mole of NH3. So that cancels out our grams of NH3. And then we were trying to convert it to the amount of reactions that happened. So we said that in every reaction, in every 1 mole of reaction, there were 4 moles of NH3 that were used up. Okay, and you can set this all up in one step just like that. This is my preferred method. So in your calculator, you would do 10 divided by 17.04 divided by 4. To get 0.147 moles of reaction. Exact same number as before. And I'm just going to show you the setup for the O2 as well. If we're starting out with, what was it, 20 grams of O2, then exact same process as before. We want to convert to moles of O2 before we can do anything. So grams of O2 cancels out. Then we want to convert to moles of reactions. So for every 1 reaction that happens, according to the coefficient, 5 moles of O2 are used up. So moles of O2 cancel. Then in your calculator, you do 20 divided by 32 divided by 5 to get 0.125 moles of reaction, the exact same numbers as before. So I like this method better because it's just faster. If you feel shaky with longer dimensional analysis problems, it's fine if you do it in 2 steps, as long as you gain the right answer and you feel comfortable with that. Excuse me. Okay, let's try a few more limiting reactant problems here. How many do we have? Okay. So, example 1. Let's find the limiting reactant if 250 grams of calcium carbonate. Okay, calcium carbonate, I'm pretty sure that is this CaCO3, is reacted with 100 grams of hydrochloric acid. Okay, hydrochloric acid is HCl, as shown in the reaction below. Okay, and we have our balanced chemical equation. Awesome. So to figure this out, I would do the same process as before. Let's figure out how many moles of reactions can be powered up by each amount of reactant that we have. So I'm going to start with the 250 grams of calcium carbonate, the CaCO3. And whenever we have grams, often we probably want to convert it to moles first. So we got to divide it by the molar mass of CaCO3. So if you're looking at your periodic table, you would add up the atomic mass of Ca plus 1 of those Cs plus 3 of those Os. So let's see, molar mass of our calcium carbonate should be about 100.09 grams in every mole of calcium carbonate. Okay, and then we got to figure out how many moles of reactions, how many reactions happen here. So in every mole of reaction, it looks like our coefficient is just 1 here. So only 1 mole of CaCO3 is used up. And calculating all of this, all we have to plug into our calculator is 250 divided by 100.09, and we should get about 2.5 moles of reaction that occur based on the CaCO3 that we had. One more reactant we got to check though, 100 grams of HCl we got to figure out how many moles of HCl that is first. So in 1 mole of HCl, Got to add up the mass of an H and a Cl. And we should have a molar mass of about 36.46 grams of HCl in each mole of HCl. So grams of HCl cancels. And now we're trying to get to from moles of HCl to the amount of reactions that happen here. So it looks like 2 HCl moles are used up in every single mole of reaction. So we're going to say 2 moles of HCl are used up in every 1 mole of reaction. Moles of HCl cancel here. And now we can calculate this. I would put 100 divided by 36.46 divided by 2 into your calculator. Let's see, 100 divided by 36.46 divided by 2. And I'm getting 1.37 moles of reactions that happen due to the 100 grams of HCl that we had. So what's the limiting reactant? HCl, of course. It's always good to make sure at the end of these problems you actually label, hey, this is the limiting reactant. You can't just do the math and leave it there. So we're going to write down HCl is limiting reactant. Okay, second example. Find the limiting reactant if 200 grams of octane is combusted in the presence of 500 grams of oxygen. Okay, 200 grams of octane with 500 grams of oxygen. And oh no, we have to balance this first. So let's go ahead and try that out, balancing this, of course. Okay, I'm thinking, okay, we have 8 C's here, so I'm going to put 8 there. What else? Okay, we have 18 H's there, so I'm going to put 9 there to get the 18 on the right side as well. And then counting up the O's on the right side, it looks like we have 16 plus 9 is 25 O's. So to balance that, we need like what, 12.5? Obviously, we can't have 12.5, so I'm going to multiply every single coefficient by 2 to get to what we want. So that's going to be 2. That's going to be 25. This is going to be 16. This is going to be 18. So that's how I would balance it. Let me know if you find an easier way. But just walking through, that's how I start balancing combustion problems. So here's a balanced chemical equation. Let's figuring out what the limiting reactant is. So we have 2 amounts of reactants. Unfortunately, they're not in moles already for us. So we got to figure out how many moles of each reactant we have. Starting with octane, 200 grams of octane, C8H18. Converting that to moles of octane. So 1 mole of octane should have a certain mass there. So I'm going to do 12.01 times 8 carbons plus I'm going to do this in a different calculator. 1 sec. So 12.01 times 8 plus 1.01 times 18 is what I did to get a molar mass of 114.26 grams of C8H18 for every mole of C8H18. Not done yet though. We have to figure out how many reactions happened. So it looks like the coefficient for C8H18 is 2, so we're going to say 2 moles of C8H18 were used up in every 1 mole of reaction that happened here. Those cancel, and we got to calculate this. So in a calculator, I would do 200 divided by 114.26 divided by 2 to get 0.875 moles of reactions or so that happen here. Okay, now we got to look at oxygen. So let's do that. 500 grams of O2 is what we start with. Always try to get to moles first, helps a lot. So in 1 mole of O2, there are, let's see, we said 32.00 grams of O2. Okay, grams of O2 cancel. And then we have to figure out how many O2s are used up in every single reaction. Looks like it's right there. 25 moles of O2 are used up in every 1 mole of O2. So moles of O2 cancel, and we can now plug this into our calculators. Let's see, 500 divided by 32 divided by 25. I'm getting 0.625 moles of reaction. Okay, so which reactant was limiting our reaction from going further? O2 is the limiting reactant here, which means C8H18 is an excess. All right, problem from start to finish. I think we have another example here. I'm gonna go ahead and do that one. Oh, this was the other example. Okay, next page, one more concept. So we talked about limiting reactant, we talked about how to find it just based on converting things into moles of reaction that happen. It's probably the easiest way to do it. It's actually an easier way than they do in AP chemistry sometimes. Back in the day, they used to actually calculate how many grams of every product you would form in order to find out what product is limiting. But in this case, this is a lot less steps. This is probably the easiest way you can do it. But the one final thing that you have to be able to define here is what a theoretical yield is. So theoretical yield, you could think of that in theory, how much will I yield? How much will I make? So the theoretical yield is the maximum amount of product you could possibly produce given a certain amount of reactants. So for example, maybe to make my ham sandwiches from before, I needed 2 slices of bread for every sandwich and 5 slices of ham for every sandwich. And let's say that I have 4 slices of bread total and I have 10 slices of ham total. So in theory, based on those ingredients, I can probably make 2 sandwiches. I mean, it seems logical, but maybe in the process of making those sandwiches, I accidentally drop all the ham on the floor and it gets dirty and gross and I cannot eat those sandwiches anymore. I did not make all that I could, but in theory, I could have made more. It's just like in reality, maybe I didn't make the most sandwiches that I could. Very similar things happen with chemical reactions here. You can only find the theoretical yield after determining the limiting reactant, because the limiting reactant is what we base all of our theoretical yield calculations on. So if every single atom of reactant reacts with another until one runs out, that theoretical yield is the mass of your product if all of your atoms react. So maybe like our theoretical yield here was whatever mass of those 2 molecules were that formed. Okay, let's see. We have 2 more examples here. So, example 3. Okay, yeah. Example 3, sorry. A sample of 10 grams of ammonia is mixed with 20 grams of oxygen. How many grams of nitrous oxide is produced? So that, what is it? NO, right there. A balanced chemical equation is given below. So when a question gives you 2 amounts of reactants, that's your automatic clue to figure out, I need to figure out what's limiting based on my balanced chemical equation and my procedures. And then once you know your limiting reactant, you can figure out the maximum amount of a product that you can make just using our mole ratio concepts here. So this looks familiar. So I'm going to look back here. We have 10 grams of ammonia and 20 grams of oxygen right here. And the same exact chemical equation, we said that, what did we say? We said ammonia was an excess, and we said oxygen, O2, is limiting us here. So let's actually use this amount of oxygen. Whatever your limiting reactant was, in this case it was oxygen for this reaction, whatever your limiting reactant was is what you're using to solve your problem here. So what I'm going to do is I am going to start from here. I'm going to start with finding my limiting reactant. And from finding your limiting reactant, you know that 0.125 moles of reaction occurred here. So I'm going to start with that amount of reactions that happened. I love this unit because you could do things like this. 0.125 moles of reaction that happened. How many grams of nitrous oxide is produced here? Well, in every 1 mole of reaction that happens, every chemical equation, it looks like we have, what is that, 4 moles of nitrous oxide, that NO, that are formed. And then we are asked for mass, or how many grams, so we got to do one more conversion here. In every 1 mole of our NO, there's a certain mass. Let's see, molar mass is mass of nitrogen plus oxygen. That's 14.01 plus 16. What is that? 14.01 plus 16 is 30.01, right? I should stop trying to do mental math and then double check myself. Yes, I was right. Okay. Grams of NO in every 1 mole of NO. Okay, so let's calculate this really quick. If we know that many reactions happen, then based on a limiting reactant, which was O2, we are proceeding forward and we're figuring out how many grams of NO that can be formed. So in my calculator, I'm literally just going to do 0.125 times 4 times 30.01. And I am getting a very nice, very clean 15.0 grams of NO that could be produced in theory. That's a theoretical yield. I mean, you know, along the way, maybe disaster strikes, maybe lightning strikes the lab, or maybe the reactants don't want to all, like, you know, collide with each other to form a product. You know, all these things could go wrong, but in theory, if everything is perfect, 15 grams of NO could be formed. All right, final example. A student is responsible for extracting copper from copper sulfate in a recycling plant. Okay, big responsibility. The student mixes 50 grams of copper sulfate with 500 grams of zinc in an aqueous solution according to the chemical equation shown below. Okay, so it looks like CuSO4, copper sulfate, plus Zn, zinc, makes our zinc sulfate, ZnSO4, and copper solid, Cu. What is the expected theoretical yield in grams of solid copper that can be extracted from the solution? Okay. So let's figure out our limiting reactant, and based on our limiting reactant, let's figure out the theoretical yield of solid copper in grams. So, okay, first things first, limiting reactant. Let's start with these amounts and figure out our limiting reactant. 50 grams of copper sulfate. Let's say copper sulfate was the CuSO4. We gotta figure out how many moles there are first. So 1 mole of CuSO4. has a certain number of grams of CuSO4, which I am totally going to figure out right now. Let's see, the mass of a Cu plus the mass of an S plus the mass of 4 O's should get you about 159.61 grams of copper 2 sulfate. Okay. And now we are trying to figure out how many reactions does this power. In this case, this is super easy. In every one of these chemical equations, it looks like there's just one copper 2 sulfate. So I'm going to put 1 mole of CuSO4 is used up in every reaction. So let's see, our units are canceling except for moles of reaction. And in our calculator, we can go ahead and plug in 50 divided by 159.61, I think that's it, is equal to 0.313 moles of reactions or so. Something like that. 500 grams of zinc. We've got to check that one out as well. So 500 grams of zinc. Let's figure out how many moles of reactions this powers up. So in every 1 mole of zinc, there is a certain mass of zinc. Got to figure out that molar mass based on a periodic table. I'm getting 65.38 grams of zinc in each mole. And according to our balanced chemical equation, it looks like the coefficient is just 1. So in each chemical, in each mole of reaction that happens, 1 mole of Zn is used up. Let's see, it looks like our units are canceling, and we can go ahead and plug in our numbers. 500 divided by 65.38, I think that's it, is equal to 7.65-ish moles of reaction that happened. Okay, what do you think our limiting reactant is? I think this one's pretty obvious. It is that smaller number based on the CuSO4. So CuSO4 is our limiting reactant, which means we are going to use that to figure out our theoretical yield. So my shortcut that I like to use is I like to just figure out, I like to start with the number of moles of reaction that we had, and just go from there. So that many moles of reaction make how much copper? How many grams of solid copper? So in one of these reactions, it looks like there's 1 mole of solid Cu, solid copper formed. One last thing, it's asking us for grams, so let's do one last conversion. In 1 mole of copper, how many grams of copper are there? Looking at that periodic table again, molar mass of Cu should be about 63.55 grams of Cu. So plugging this into a calculator, I would plug in 0.313 times 63.55 to get about 19.9 grams of copper formed from this reaction. In theory, that's a theoretical yield. I don't know, maybe only 5 grams are formed, but in theory, according to our calculations, 19.9 grams are formed. I just rounded it a little bit. All right, that was my lesson for today on limiting reactants and theoretical yield. Mr. Schleicher is now over and out.